Hello. In today's lecture, we're going to be going through tutorial 8, which was looking at a mass on a spring. Okay, so a quick recap on what the system looks like. So imagine we've got some kind of wall with a smooth surface, so no friction. Then we've got a spring with like a box or some kind of mass M. And the spring has some spring constant K. So if we extend this mass away from equilibrium, okay, then we're going to end up with the following. Okay, so let's stretch it out. Still mass M. Okay, and then this distance from equilibrium we're calling x. Okay, so when x is 0, then we're at equilibrium. If x is greater than 0, then we are stretched away from equilibrium. If x is less than 0, that means we're on this side over here, which means it's being compressed. Okay. Okay, so what is the net force on the system here? Well, we've got Hooke's law, and it says that the net force is given by F net is minus Kx. Yeah, where we have this minus sign because the net force is in the opposite direction from the displacement. So if we displace this mass to the right, like we're doing here, then the net force will be to the left so that it brings it back to equilibrium. If we compress the spring so that we're applying a force to the left, then Hooke's law says that the spring will try and expand again to bring the mass back to equilibrium. So the force will be to the right. Okay, so it's always in the opposite direction. So that's why we got the minus sign there. Okay, so if that's the net force, then we can find the equations of motion using Newton's second law. So F net is equal to ma. So we have mx double dot is equal to minus kx. Okay, rearranging a bit, we get x double dot plus k over m x is equal to 0. And usually we make the definition of omega squared is equal to k over m. Okay, the frequency of oscillation, omega. Okay, so x double dot plus omega squared x is equal to 0. And we've seen this equations many times now. That is for simple harmonic motion. Yeah, so we can solve this analytically. We've done it many times now, but we want to solve this computationally so that we can do a bit more investigation into the system. And usually in physics, we convert some complicated system into a simpler system to work with at first. So if we have some complicated potential, we can approximate that as a quadratic potential, okay, which comes from Hooke's law here. Remember U being proportional to x squared, that's the potential here. So if we have some complicated potential, we can usually approximate it as quadratic as a starting off point, and then we can add complexity later. So it's important to understand these simple systems. Okay, especially computationally, because as we add more and more complexity to the system, it may not be solvable analytically. So then we're kind of stuck with approximations or using computational methods. Okay, so it's good to understand these simple systems. Okay, so what we can do is turn this second order differential equation into two first order differential equations by introducing another variable v, which is going to be given by x dot. Okay, similar to what we did in the previous tutorial. So doing that, we're going to end up with v dot, that's going to be x double dot, is minus omega squared x. Okay, and we can think of this as a function f of x, v, and t. Okay, in general. Then we have x dot is just going to be v by definition, but we can think of this as a function g of x, v, and t in general. So we've got two first-order differential equations that we can then solve. So in the tutorial, you're supposed to be solving them using the Runge-Kutta fourth-order method. Okay. With initial conditions being x naught is equal to L and v naught is equal to naught. Okay, so these are our initial conditions. Okay, and then L is specified by the user. So you're going to have some sort of input prompt to get that from the user. Okay, so with those initial conditions and knowing the updating procedure, as well as the two first-order equations, we can then solve for x and v as functions of time. Okay, so that's the standard thing that we did before. So what we're going to do now is try and do a bit of investigation into the system. Okay, so looking at properties of the system, like the energy of the system. Okay, and how the energy changes with time. Okay, so that's question 3 on energy conservation. Okay, so what we want to do is find the kinetic and potential energy independently, and then plot those two to see how the energy is moved from being stored as potential energy to being stored as kinetic energy. Okay, so the total always remains the same because there's no friction, but the energy does move between those two energy storage units. So it goes from potential to kinetic. So we can imagine it as like something like this, where we have kinetic and potential. So we start off having maximum potential and no kinetic, so that's 0. And then over time, we have the following. So the potential goes down. Okay, so that means the mass is moving closer to equilibrium, but as it moves closer to equilibrium, the kinetic energy will then go up. Okay, and then as it moves past equilibrium, the kinetic energy will be at a maximum because it's moving its fastest as it goes past the equilibrium, and the potential will be 0 because it's going to be at equilibrium. So there's no force acting on it at that point. Okay, so no potential and maximum kinetic. And then this process repeats. Okay, so it's constantly moving between the two. Okay, so how do we find this? Well, the kinetic energy, that's the standard half mv squared. Okay, and v, that comes from solving the first differential equation here. So the first one is for v dot. If we solve that, we get v of t. And then if we solve the second one, we get x of t, and we can use that to find the potential. It's going to be half m omega squared, x squared. Okay, but since x and v depend on time, we're going to have k of t is going to be half m v of t squared, and we're going to have u of t will be half m omega squared x of t squared. So individually, the kinetic energy and the potential energy depend on time. However, if we add the two together, we get the total energy, E, and that does not depend on time. So this U plus K, that's time independent. Okay. And then for question 4 of the tutorial, you're going to be solving them analytically. So solving the equations of motion that are boxed here. You can solve that analytically given the initial conditions, and then you're going to compare your solutions that you found on paper with those that you found on the computer. Okay. And there's a little bit there on what do you notice about the two solutions. You should notice that they match up quite well. Okay, but make the plot and just check. Do you get that sinusoidal behavior? Okay. So tutorial 8 is fairly simple, just a bit of programming. And just notice that a lot of this is repeat from tutorial 7. So all of this work on solving the system, if we define these functions f and g, like we did with the Runge-Kutta method, if we define those functions, then we can copy the code, just change the functions. So this f, that will change a bit, and this g, that will change a bit. But the actual procedure, the actual implementation of the Runge-Kutta method, that's exactly the same. Yeah. It's just these two equations here and the initial conditions that change. Okay, so you don't have to redo everything. Try and make it general the first time you're writing the program, and then you can just change a few things when you're changing the system. Okay, so just something to keep in mind. Okay, so that's it for tutorial 8. Remember that that is due next Monday. Okay, so we will go through this again on Wednesday, so you'll have some time to use the computers on campus to go through this, but then your final submission needs to be made on the Monday. Okay, if you do have any questions, please feel free to ask. Okay, so I'm here to help you with these tutorials. Okay, and then I'll see you on Wednesday.